I'd like to welcome everybody back. I hope you had a good break. What we're going to do now is continue on with our discussion about science and how to conduct science. Now, conducting this experiment on how vitamin C affects the duration of a cold does not sound very difficult, does it? You know, you just get some folks together who have a cold, or you give them a cold, you give them some vitamin C, stand back and see what happens. Well, as you can probably imagine, it's not that easy. The experiments that we design have to meet certain standards or criteria set by other scientists to ensure that we do not screw up and determine that the vitamin C is beneficial when in fact that it is not. And you would think that giving someone vitamin C would not be that big of a deal, and it's not. Vitamin C is good for you for a number of reasons, but let's say that we conclude that a new cancer drug is safe when in fact that it is not. In this case, it could actually cause people to die. So the design of our experiments can be pretty darn important. In general, you want your experiments to control as many things as possible before you test your hypothesis. With our vitamin C and cold example, if some of the people are taking other cold medicines or cold remedies and not telling us, then that could completely screw up our results. These type of experiments are not always possible. For example, how do we know how life started? We can't go out and create several planets and conduct controlled experiments, but we can make observations about the natural world that seem to hold every time we look. And we'll talk a bit more about this type of experimentation later on, but you just have to understand that there are other ways at getting at some of these answers without doing the type of experimentation that we're kind of talking about with this kind of classical way of conducting science. We also may make smaller experiments to test part of our larger scientific theory. And again, that's kind of what's been done with this idea of natural selection, is they might test a part of this overall larger scientific theory to enhance the theory and maybe falsify maybe small parts of it to make us rethink it. But in general, that's how we develop this information. But if at all possible, what we want to use, or our ideal experiment type, is going to be these controlled experiments where we can have groups that get the treatment and groups that don't get the treatment, or give them different amounts and so forth. That, we want to use these controlled experiments whenever possible. Now, the information that scientists collect is called data. And these data, which is actually plural, are collected on variables of the test or any factor that can change in value under different conditions. So for instance, if we were measuring the effect of a freezer on temperature, and maybe it's got a dial and it says cold and colder on it, and we want to know, what does that really do? So our variable would be temperature. Okay, and we would turn the dial and it would cause the temperature to increase or decrease, and we would measure this. We would measure the response of the temperature on our thermometer, which would be, remember I said we had to have some way of measuring. We can't just stick our hand in there and go, yeah, it feels colder. So, this is what's going on. An independent variable is a variable that the scientist can actually change. So if we go back to our example, we can change the amount of vitamin C from 500 milligrams to 1,000 milligrams. That would be a variable. Now, the effect of doing this will change another variable, which is called the dependent variable. In this case, changing the amount of vitamin C that we're giving someone would affect the duration of the cold, or time, which is going to be our dependent variable. Go back to our freezer example. Think about it. When we turn that little dial, what does that actually do? Okay, that increases maybe the frequency that the compressor turns on. Maybe it causes more electricity to go to it. But whatever it's doing that, turning that dial, and the effect that that has, of causing the compressor to come on, that's our independent variable. So let's say maybe the amount of time the compressor kicks on is our independent variable, and then the temperature inside of the freezer is going to be our dependent variable. And then we measure that using our thermometer. A third type of variable are the things that you don't want to change between individual subjects. So in our case, these are the people who have the cold. These are called either control variables or standardized variables. Another way of looking at this is that these are all independent variables that the scientist could manipulate, but has chosen not to. Now, ideally, we want our subjects to be as identical as possible. Ideally, they'd all be genetic clones with the same sex, height, weight, eye color, diet, and everything and anything about them that could be different. We would want that to be the same, except for the one thing that we want to alter. This way, when we give some of our subjects vitamin C and the others don't get the vitamin C, the only thing that is different about these people is the presence of the vitamin C. However, in the real world, this is not possible. Sometimes it is. Sometimes, if we're using mice or other animals that are for the most part genetically identical or twins or actual clones of each other in some cases, then when we test on those things, we can control those, just the one variable that we want to. But more often than not, especially in biology, this is not going to be the case. So what we do is we control as many of the variables as possible, or try to get them as similar as possible, so that when we run our experiments, we are less concerned about the variability of the subjects causing the effect. For example, obesity or anorexia might stress the immune system, thereby also affecting the duration of a cold. So when we select our subjects, we might only choose those subjects within a normal weight range, or a range that we have specified. If we have access to hundreds or thousands of volunteers, then we may only choose those that are within a very narrow range of weights. It is critical to control any of the variables that might affect the duration of a cold. And this is something that you, as somebody who is possibly trying to evaluate the validity or how well a bit of science has been done, if you look at it and they haven't controlled for a lot of these different things, then it may the results of their project may require a little bit more scrutiny, because they might have not done everything they needed to do to make sure that when they gave them the vitamin C, in our case, that was actually what caused the effect. Now, in reality, there are always things that we cannot control for. We address this by having control groups for our experiment and randomizing our subjects between these control groups and the treatment groups. Okay? Now, be aware that this is distinctly different from our control variables, okay, or the standardized variables. So we've got these things called control variables, which are the variables we do not want to affect, and we have control groups. Okay? The way to think of control groups is, remember, we've got all these control variables. The control groups, all the control variables are the same, and that one independent variable that's going to be our experimental variable, we don't do anything with that either. Okay, so basically the control groups, they don't have anything done to them, or they don't get the treatment that the other groups get. They may have something done to them, and you'll see what we're talking about in just a second. But the experimental control, or the control group, is identical to the subjects of the experiment. So in our case, our control group is going to be those people who do not get any vitamin C at all. So we've split them up into two groups, and we've got people who get vitamin C. That's our experimental or our treatment group. Okay, and then we have this other group who did not get any vitamin C, and that is our control group, but they all got colds. And those people just have to suffer with their cold for the entire duration. Okay, now if the control groups are virtually identical to the treatment groups, then the only thing that will be different is that some of the people will get vitamin C and others will not. And what this does is it eliminates confounding factors that would influence the results of our experiment. Now, as we've said, it's almost impossible to get people who are identical. So we take people who are as similar as possible. Okay, so like I said, we selected our 100 people who are similar weights and maybe all the same sex, or maybe we've said 50 of each. And then what we do is we randomly assign the treatment groups to them to further reduce the differences between our control group and our treatment group. So we say cold, no cold, vitamin C, no vitamin C, vitamin C, no vitamin C, vitamin C, vitamin C, no vitamin C, vitamin C, because it's random. And this is maybe done with a number system, randomly selected from a hat, maybe throwing dice. Whatever we do, if it's a random process, then if there is minor differences between people, it doesn't affect the results. Now, an even better design is to make sure that we treat all the subjects as similar as possible. So what we might do is, if we're giving subjects vitamin C pills, then we would give everybody a pill. And the non-vitamin C pill might be just a sugar pill, or just the coating of the pill with really nothing in it. And this is called a placebo. This way, if people think they are getting pills that is supposed to make them better, it could have some sort of psychological effect, and this is called the placebo effect. So basically, the people who get the pill, they actually believe they will get better, and their immune system kicks in, and it actually makes them better faster than it would normal. And there's no difference between the vitamin C, so it's not really necessarily the vitamin C that's making people better, but it's just the fact that they're taking something that they believe will make them better. And by giving people this pill, this fake pill or a fake shot or whatever we're going to get them, will help identify this effect. So now that we have our subjects with a cold, and we have taken a bunch of subjects and we have randomized them who will get the treatments, and we have given some a sugar pill and some 500 milligrams of vitamin C, and maybe a third group with 1,000 milligrams of vitamin C, the scientists can now sit back and measure how long each of their colds last. So let's stop here and take another break. And when we come back, we will continue on with our discussion.